I think we can start again. So in this session, after lunch, we'll have a look at the log file. Then we'll work our way through some more advanced input and output commands, stuff like how to output a trajectory, how to calculate some properties and write them to file. And then at the end of the session, we'll touch on using GPUs to accelerate simulations, as well as some extra software that you might want to use, either to prepare your topologies or to visualize your trajectories, to pack your systems, stuff like that. Okay, so let's start with the log file. This is the log file from the previous exercise where I had the density at 0.8. And as you can see, the commands that we had written on the input are all included here. So the first line will tell you what version of LAMMPS you were using and what was the decomposition of OpenMP threads and tasks. But then it starts actually writing the lines that were in the input file until LAMMPS hits something that needs further calculation. So as you see here, let's recap then. At the top, you'll see the LAMMPS version. Then LAMMPS will output all the lines in the input file until it hits something that it needs calculating. And here, that will be the density. It will get that value from the variable that we assigned above, and then it starts calculating the lattice spacing. We touched that briefly on the last section. Creates the box. The box will be 10 times the lattice spacing, and then it does the decomposition over the number of cores that we have. In this case, it's a grid that's 4 by 4 by 8, and that should give you the number of processors that I ran this with, which I forget if it was 64 or 128. And then I believe it was 64. And then it continues. Same idea. When it needs to calculate things, it does. Otherwise, it just writes the input commands until we hit the run command. And after that, it's when the simulation actually starts. And LAMMPS will calculate some initial properties and then run the simulation. So some of the initial properties will be those neighbor lists. They need to be generated at least once, although in our case, they will be regenerated every 10 time steps or so. Calculates the cutoff for the neighbor list atoms, and all of those details as well. Then it gives us a little bit of information of the average memory that it predicts that it's going to require. So minimum, average, and maximum for each of the threads. These can be one way of debugging whether your system is running out of memory. In some cases, if you're running this on your laptop, your operating system might put some of these into cache, which just means write it into disk. In ARCHER2, that probably wouldn't work very well. I don't think LAMMPS would have access to the space on the nodes, so it would probably just crash with illegal memory access or something like that. And after that information, we get our thermodynamic information that we had touched briefly before, but let's go a little bit more into detail. The first line will always be the column titles of what things we asked it to print, and then every X number of time steps that we set up in the input file, it will calculate and write those values into our log. If we were using different ensemble, for example, if we had used constant pressure, for example, we would have seen our volume changing, but because we're keeping our volume constant, that and the density will always be the same. If we had kept our pressure constant using NPT, for example, we'd see the pressure here varying a lot less, and you'd see the volume and the density varying a lot more. After the 15,000 time steps that we told LAMMPS to run, LAMMPS will output the information of how long that run command took to simulate how long it took to run in our system. So it gives us the info that it took 4 seconds on 128 cores, 50,000 time steps and 1,000 atoms. So it gives us a very nice summary of that last time step. And then a very important bit if you're doing benchmarking or if you're setting up a new system will be this table below. So from the performance line, you can get an idea of how long you'll need to run your simulation if you want, say, 1,000,000 time steps. So you know that doing 12,000 time steps per second, it's easy to get how long it would do 1,000,000 or 100,000,000 or whatever, or however many you need. In situations where you have, when you're using the real unit style, you'll also get these result in nanoseconds per day. For example, if I go to the ethanol one that we run before, we can see that the information comes in nanoseconds per day, as well as hours per nanoseconds and time steps per second. So that it gives you an easy way to calculate, well, if I want 50 nanoseconds, I'm going to have to run this for 4 days and a bit. Because we're using LJ units here, we get this tau per day, which is tau is the time unitless unit in LJ systems. And then we get breakdown of the NPI tasks. We have, again, depending on exactly your force fields and whether you have bonds or you have angles or dihedrals, this table will have more sections. In the course material, I believe that we have examples of extra fields that this one doesn't have. So bond K-space, for example, are some of those. But basically, what you're looking here is the minimum time that any of the threads used for this part of the code, the average, and the maximum. And then perhaps the most two important columns are these: the percent variability on the average and the percentage of the total. The variability from the average, the closest it is to 0, the more balanced your simulations are across the cores, and the less time some of the cores will be idling waiting for the other ones. And then the percentage of the total indicates you how much of the total time each of these sections took. As a rule of thumb, you'll probably want your pair interactions to be the majority of your time. You'll want neighbors and any K-space, if you're doing long-range interactions, to be around 10% or up to 30% in certain cases, but as low as possible. You'll want communication to be as little as possible, and as you can see here, that's not really the case. That's because our system is way too small for the number of cores that we're running it on. Rule of thumb right now seems to be roughly 2,000 to 3,000 atoms per core, and we're running 1,000 atoms on 128 cores, so that's much less than that. That's why our communications costs are so high. These communication costs will increase massively if you go from one node to more than one nodes, because then it's not just communication inside the CPU, and it's also communications between nodes across the slingshot network. So that has a larger latency. That there's always be some costs associated with that in terms of time. So you can never completely get rid of it unless you're running on just one core. But you want to try and minimize it by having enough work on each core. So that means enough atoms to calculate things on each core. And then output is when you're writing things to the file, be it the log or a trajectory file like we'll see later. Modify is all the fixes and the compute commands that you have. So things like changing the linear momentum, the ensemble, so fix NVT will be included here. So that means taking care that the temperature is constant, that, or in certain cases that the pressure is kept constant. Those costs come under here. Other is anything that doesn't fall under all of the other categories that LAMMPS shows before. So after that MPI slash task breakdown, which is very important, like I said, if you're benchmarking, if you're testing new systems, make sure that your communication isn't the majority of the time, because then you're just wasting computational time and your budget. You get a breakdown of neighbors. And this one can be a bit confusing at first, but what it gives you is the average, the maximum, and the minimum number of atoms on each of your cores, on each of your MPI threads, I should say. So on average, each of our 128 threads had 7.8 atoms. The maximum was 12 and the minimum was 5. So that means that does tell us that the balance is not very good. And then it gives you a 10 bin histogram of the number of atoms on each processor, or on each thread, I should say. So here you want, I mean, ideally you'd have one bin with all of them put together with exactly the same number of atoms. That is usually almost impossible. So if you have 2 or 3 bins with a very large number of atoms, that's usually a good sign. A larger spread like this is usually a sign of imbalance, which we can also see from the end local. The end ghost is the number of ghost atoms. That is the number of atoms that are between your neighbors and the end of the neighbor list skin that we set up in our input file. And the histogram is the same idea as above. Here it's less important in terms of balance, but it's more to check whether we're not getting a significantly large amount that we probably don't need. So if our skin is too large, you'll get your memory usage will be too high. So you might need to reduce that for particularly large systems. And then finally, the neighbors. So that would be the neighbors inside the LJ cut. So this one is under the LJ cut, and this one is above LJ cut and under the LJ cut plus the neighbor skin. And then again, the histogram is the same idea, 10 bins with the distribution. And then a little bit more information about neighbors, the total number of neighbors for all the atoms, and an average per atom. That doesn't usually tell you a lot unless the values are extremely low or extremely high, and then you might get suspicious that something happened. Then we get how many times the neighbor list was built. Because we had a delay of 10, the maximum of rebuilds would be 5,000, but because on the last time step it won't rebuild it because you won't need to run it again, we get the 4,999. And then the number of dangerous rebuilds here, which is almost all of them. This means that between each rebuild, there was at least one atom that moved more than our neighbor skin. That means that our neighbor skin is too slow or that our delay is too high. Ideally, you would change those around so that your dangerous builds are 0. Dangerous builds means that the physical properties of your system might not be 100% correct, because you might have had an atom that was not in the neighbor list moved inside your cutoff and wasn't being properly summed into all the forces. So your system might not be 100% physically correct. And then the last line is your your wall time, so how long it took for the entire thing to run. The difference between the wall time down there and the time here is that this one is just for the run command, and this time here is for all the commands in your script. You might have several run commands inside the same script. You can change your ensemble between run commands. You can add different computes, anything like that. So the last wall time will give you a total runtime of the entire thing, and each run command will then have how long it took for that one command. Okay, are there any questions about the information in the log file that maybe I didn't explain very well? Okay. If there's no questions, we can move on to advanced input commands. And to do that, we can have a look at the files in exercise 3, and we will start with this one. This one is very similar to the previous exercise file. What we are adding here are these 4 lines here. The dump file is the command that LAMMPS uses to write a trajectory file to disk. The syntax is very much similar to other commands with the ID first. So this would be a unique identifier for dumps. You can have several dumps writing different types of atoms, for example. So if you have, let's say, a nanoparticle in a solvent, you can write the trajectory of the particle independent of the trajectory of the solvent atoms if you so wish, or you can keep them all together. So the group ID will be to differentiate those, and then if you do any sort of modification to the dump file, you need to identify them by that ID. The ID can be alphanumeric. Here we just have one, but you can call it, dumping all files or something like that, and then just reuse that identifier elsewhere. The second thing will be the ID of the group that you want to use. In this case, all is a default group that LAMMPS always creates. That means all the atoms. You could specify by type, or you can create groups by region using the LAMMPS syntax. And usually specifying by atom type might be the easiest thing. So like I said, for the nanoparticle example, you would separate by atom types of the solvent and the atom types of the nanoparticle and dump them separately if you wish. Then we have the custom, that is the style of the dump. That just means that we can choose exactly what types of information we are writing to disk. Then we have the frequency, how often we write that information to disk. This is in time steps, not in time units. So every 100 time steps, we'll be writing information of the simulation to file. Then you have the name of the file. I'm just calling it nvt.lampstrj for trajectory. This is a fairly common suffix for trajectory files of LAMMPS. It is recognized by a lot of the tools that we'll touch briefly on later, like VMD and the analysis and stuff like that. So using a known file extension might help you later when you're trying to load it into some other program. And then because we did custom style, we can then choose what kind of information we want to write. In this case, we're choosing to write the ID. That is a unique identifier for each particle or atom. They'll be numbered from 1 to the total number of atoms. And they are not necessarily in order, in memory. So they'll be dumped in a random order that we then tell LAMMPS to sort. So this is what this dump modify does, is it goes through that on each time step, it will reorder the atoms so that they are ordered by their atom ID. We then have back on what information we're dumping, we have the type, that is the atom type. In the case of the LJ, we only had one type, but in the case of ethanol, for example, you'd have several carbons, a few hydrogens, and the oxygen. So those will all be different types. By default, LAMMPS will also assign numerical types to them, starting at 1. And then we have X, Y, and Z positions, and then velocities in X, Y, and Z directions. There are many things you can write to disk using the dump command. I'm afraid you'll have to have a look at the LAMMPS manual to have a complete list of all of it, but there's quite an extensive list. Then, so this is how you get a trajectory, for example. If you want to calculate something, you'd use the compute command. Before we do that, let me just run that exercise so that we can have a look at the output of it in a minute. Okay. So we'll touch on restart files in a second, but you can compute properties in LAMMPS at the same time that you're doing the first run through of your simulation, or you can compute them afterwards if you have a trajectory with enough sampling. That is, so depending on how big your systems are and how often you can afford to write down, you might want to do some of the calculations at the same time that you are doing the initial run of the simulation. But sometimes if you just want the last positions or something, you might be better suited doing that on rerun or just at the end after the simulation ended. The compute commands is the same and allows you to do it either way. Here we're just calculating a radial distribution function. So this is it describes the density of particles and how that varies as a function of the distance between a central average particle. So if you had an extreme homogeneous system, these RDF would always be 1 because it's a distribution function, so it's a probability thing. And when you have higher concentrations than an ideal homogeneous situation, you get values of RDF above 1, and when you get systems that are less dense than that, you get values lower than 1. And this is done as a function of distance from the center of the atom, and we can have a look at how this looks for the Lennard-Jones system as soon as this finishes. That's done. Okay, so we have GNU plot available. Oh, I don't think you even need a module. Maybe you do. Ah, there we go. With the module, we have GNU plot available on ARCHER2, so we can quickly plot some functions from this data. The RDF was written to this file. So if we open GNU plot and tell it to plot there we go, this was on the wrong window. So if we tell GNU plot to plot the radial distribution functions, we'll see that there's a very dense peak at around 1.1 units from the center of your average atom. That is what is usually called the first shell. Then there's a void, and then there's a second shell, another void, and a third shell. These RDFs will vary wildly between substances, between how they interact, and as well as the state of matter that your system is in. And they're a very useful tool in a lot of scientific identification of systems, and even to tell what types of atoms tend to aggregate together. For example, in this system, we're just calculating between the same type of atom, but an RDF could be calculated, for example, between all types of polymer atoms and the solvent atoms, and that would give you a RDF that would be wildly different from this one, and you can tell a lot from that. The syntax here, it starts very similar to the dump and to the fixes, where you have an identifier for the compute. And this is what you'll use if you want to override it or to stop the compute at some points. Then you have the ID of the group of atoms that you want to calculate the RDF on. In this case, it's all of them. And then the type of compute, in this case, RDF. There are many compute types. I'll grab the LAMMPS manual on it. There are an incredibly large number of things that LAMMPS can calculate by default. These can also be expanded. But if you want to calculate something about your system, chances are there's a compute already ready for it, or that can calculate it. There's, like I said, a very large amount of them. The compute command only tells LAMMPS to calculate the things. It doesn't tell LAMMPS how to write it to file. For that, you need another fix. You could write the RDF for every time step and do your post-processing analysis afterwards, or you can ask LAMMPS to calculate a running average and only give you that. You could ask for an average for the entirety of the run, or you can use these average/time fix to calculate every X amount of times, for example. So the syntax here is kind of weird and can take a while to get used to, but this is explained, I think, fairly well in the manual. But what we have here, besides the usual fix ID, what group of atoms we're calculating things, and then the name of the fix, we have these n-every, n-repeat, and n-frequency values. The n-frequency values is how often you want to write a value to the file that you define here later. So this means that we're only writing to file every 50,000 time steps, which in this case is the entirety of our run. You could write every 10,000, for example, and then you'd get a file that would have 5 different RDFs at every 10,000 steps. What the n-repeat and n-every cover is how many averages I want to save to average over for these right, and then how many time steps do I want to wait between I take a sample. So this is basically the number of samples and how often I sample for the actual time I write. It can be very confusing. I always need to check the manual before I use this. Some important details is that n frequency, so that the last value needs to be a multiple of n-every, and every needs to be non-zero, even if you're only doing one repeat, which is a weird caveat of LAMMPS. So even if you're only doing one sample, and every still needs to be non-zero, which was a bit weird for me the first time I saw. So we have an example on the course material that would be if n every was 2, and n repeat was 3, and n frequency was 100, you'd get 3 samples at time steps 96, 98, and 100, average that and write to file, and then you'd get another sample run at time steps 196, 198, and 200, and then that would keep going with that same pattern until your run would end. I understand this might not make much sense. If there's something I can help here, do let me know. But this is one of those things that you need to have a go, and we'll have a chance in a little bit if you want to have a play with these numbers for the RDF. The final thing at the end here is the how you're writing and where and in which way. This is confusing. So on this C_RDF, this is LAMMP syntax for the values of a compute. So that's why it starts with C. And then this star means to write all the values in that. This is considered internally as a vector, as a list. So just write all the values in that to the file, and then the name of the file is rdf_lj, and then we're using that density variable that we set up at the start of the input file. And then the mode is vector, again, because of the syntax that we use here. These options will change with what you're calculating. The compute page about on the LAMMPS manual will usually have an example of the fix that you should be using to write the data. Before we have a look at the trajectory file, let's just have a look at the RDF and see how it looks. So the RDF file will output a bunch of data at the top. So some string telling what it was, and then the information that it's going to print later. So this first line is referring to this one. So time step. So this is the number of the time step that it wrote on, and then the number of rows that it wrote. So that would be 150 different bins, as you can see here at the bottom left. And then this last commented line is the titles for the columns that start here on the second. So this would be the row number, and then CRDF 1, 2, and 3. So that's all the information on that vector. These are explained in the LAMMPS manual, but these are the distance from the atom, the column 3, which is CRDF2, will be the actual RDF, and then the last one is a oh my god, the name escapes me now. It's an accumulation of the number of atoms from the start. So it's a count from the start. You see here, the first bit is all zeros, and then we start at 0.8 to get an actual numbers for RDF, and then until all the end. And this is what I plotted earlier. If we have a look at the dump file so that you see what it looks like, the LAMMP file will have a little bit of a header. Here, it will start with these labeled lines with item : space, and then with the information about it. So this item time step, it tells you what time step the simulation was on, and then it tells you how many number of atoms the simulation had, what were the bounds of the simulation box, and whether they were periodic or not. So that's what those 3 pairs of keys means. These are periodic conditions. And then below you get the X, Y, and Z, the minimum X, Y, and Z of your simulation box. So between 0 and 10.7 in every dimension. And then the last section for each time step is the actual items. So get item atoms, and then it tells you the titles of each column, basically, which was what we requested in the dump command with the custom dump style. So it would be the item ID, the item type, positions in X, Y, and Z, and the velocities in X, Y, and Z. And because we had that command that sorted by ID, you can see here that all the atoms are sorted in increasing order by their atom ID. The second column, again, would be the atom type, because of it's an Lennard-Jones system, and so they're all the same type. So it's all one, and then you get your X, Y, and Z positions, and then the velocities in X, Y, and Z as well. Is there any questions about either the RDF or the dump file? Okay, if there's no questions, I would suggest a very, very quick exercise. 10 minutes should be more than enough, so until 2:50. If you, on the folder exercises 3, so this one, advanced inputs exercise, if you check this file in .lj_exercise, and if you change the density up here, I would suggest 0.8, 0.05, and maybe 1.5 or something like that. Run it those 3 times with the three varying densities. That should create 3 different RDF files here with the density in the name, and then have a look using gnuplot on how the RDF files look. I'll paste the how to plot the files with gnuplot on the chat in a second if people have not used gnuplot before. Okay, so that's the 3 different RDFs at 3 different densities, and have a look at the gnuplot outputs. Got another 8 minutes for this. Yes, James. You can change the 0.8 to a different density if you run the input at different densities. But yes.
Okay, I get an error that says it's trying to plot with an unknown terminal, and it recommends me to select the terminal. Yeah.
Okay, that might have to do with the terminal emulator that you're using, and maybe SSH not being started with -X. That usually works. Yeah.
Okay, I mean, yeah, I'm using Windows subsystem for Linux.
Yeah, same as me. The difference here, you can try this, the -X command there. That is right. Yeah. Cecilia, that does depend on what you mean past months, how long that is, and what kind of changes you're talking about. So what you can do is copy your RDF files to your laptop or your desktop or your local computer, and then trying and launching gnuplot from there, or using a different plotting tool. But yes, the SSH-X and then the exact same command you'd use should, in most cases, allow you to get the gnuplot. Oh wait, if you're using Windows, you'll need Xming, I think it's called. It's an X Windows server. I thought we had that on the setup instructions. I'll double check, and if not, we'll add that for next time. If you have Mac, it would be Xquartz, I think, and if you have Linux, it should be set. Anyway, I can show you what it looks like. You have seen this one. Let me. So that would be the same we saw a few minutes ago, 0.8. If we now do, yeah, Anthony, that is correct. Would you care to hazard a guess as why you see more structure with higher density? Now, this is what it looks like at higher density. I used 1.5, but I think anywhere from 1.4 upwards would show similar things. Would anyone like to make a guess? So on Lennard-Jones systems above 1.4-ish density, what you get is the equivalent basically of a solid. So that's what we're seeing here, is a kind of, it's mostly amorphous, but you'll start to see that kind of structure on the RDF. That's why we see a lot more structure, a lot more shells and peaks and valleys. And the opposite for the very low density, which is just basically a gas. So that's when you get some low range interactions, but then at higher distances, you just basically just have random distribution noise, basically. So that is basically what a gas looks like in a Lennard-Jones system. Okay. So imagine, for example, that you want to do a very large run, so many time steps, and the time that it's going to take is going to be, I don't know, a week. The queue system on ARCHER2 will not allow you to submit a job that long, so you'll need to split it into several parts. LAMMPS has a very nice way of dealing with that. They're called the restart files. What you can do is you create an input file with a smaller number of time steps. You tell it to run, so for example, 24 hours, and then at the end of that, you write a restart file. And then you can create another input file that reads that restart file and then continues the simulation from the point where it stopped. restart files can also be used as they're commonly colloquially known as checkpoint files. So you can write a restart file every X amount of time steps. So then if your simulation crashes, or if you're running it on your laptop, for example, and your desktop crashes or something, your progress will be saved. You can continue from the last restart that you saved. Be aware that writing a restart file has some cost in terms of time. It takes some time for the system to write everything to disk. So don't do it too often. Otherwise, you'll spend more time writing the restart file than you will doing actual simulation. We've got an example on how that does. So here at the end of the main file, we have a write restart. So that means that at the end of the simulation, after the 50,000 time step run, LAMMPS will write this restart.lj.equilibrium restart file. This is a binary file. You won't be able to read it like we do for the trajectory files. This is a binary, but LAMMPS will read from it a lot of the information that it needs to continue the simulation. What details are included and which ones aren't changes from version to version of LAMMPS. So you shouldn't really use a restart file from between LAMMPS versions, and you probably shouldn't use a different number of cores either, because the way that the binary data is structured depends on the number of cores that you started the simulation with. If you want to do that, I would recommend you write a data file instead, and we have an example on the course material. But instead of a write restart, you'd have a write data, and then you can give it a name. So it just takes a name, and then this would write a LAMMPS data file that includes the information on atom positions, on any bonds, angles, and dihedrals if they have them, as well. No, nothing else. That's it. It does not include velocities, for example, which the restart file does. So it's not I mean, it doesn't. It's not as good as the restart, but in a pinch, if you need to change systems, for example, it can be quite useful. To continue from a restart file, we have an example here from the restart. The first thing you should do is to read the restart file, and that will load all the atoms, positions, and velocities, and whatever. And then you need to set up several of the things. I think most fixes will not be saved on the restart file, so you need to set those up again, and that would include the ensemble and the thermostat. In this case, we're changing to the NPT. So after the equilibration that we did at constant volume, we're going to apply some pressure, some 1.515 units, and then you need to set up again your time steps, thermostyles, your dumps, and then you can also do some compute. So in this case, we're gonna be having a look at mean scattering distance of this system. Sorry, mean square displacement. What am I saying? The syntax here is pretty much the same as the RDF, although instead of being a time correlated function, it's a position correlated function. So it has the slightly different fix command, but the variables after that, the flags after that, are pretty much the same, or the fields after that. So we should have a restart file here from the previous one. We do. So if I launch the restart, it should. Oh, yeah, never mind. I need to change the S batch to use the restart. So I'm now telling you to use the restart input file and to write the log to a different place. That should work. That might take a second. should be done. So if we have a look at the restart log, it will be very similar to the original one. We'll see that it read the restart file, and it tells you that it's reading the restart file. It tells you how it the version of the restart file. So this is, I guess this would work with versions of LAMMPS 23 June onwards. So you have some compatibility there. It's reading the box, doing the decomposition, the same things as it would have with the regular input from fresh, doing the reading all the input commands, again generating neighbor list information. And then here on the thermodynamic, you'll notice that it's now starting at time step 50,000, because we had already run 50,000 time steps on the first input file. And now we're continuing from that 50,000 time step mark, and we're doing further 50,000 time steps, now using the NPT ensemble. So you'll see here that the pressure and the volume and the density will be changing now. And we're not fixing the volume of the box anymore. And then after 50,000, so the last time step will be 100,000. We have exactly the same kind of information that we did the previous time. The final thing that you might want to know about in these input output read things is what's usually called a rerun. And this is when you read a trajectory file and calculate things from it. So in this case, you need to set up a lot more things than you would have with the restart file, including the pair styles and all of that. And instead of run command, you use a rerun command. But then when you, if your dump is not is using the custom style, you also need to tell it what kind of information it should be reading, which is the XYZ, VX, VY, and VZ. But then what you can do is run compute commands on atom positions that are already calculated. So this is extremely fast. So if you save the trajectory file and you forgot to calculate some property, with the rerun command, you don't need to run the simulation again. You can just calculate that property on the data that you already have. And that is incredibly quickly. And you can usually do this, unless your system is massive and the memory requirements are very large, you can usually do this very quickly on a single core on your laptop. So in some cases, you might want to do as many computes as you can when you run the simulation. But if you forgot something, this is one way of quickly calculating something from the trajectory file. That is the last thing I think on this section. Could quickly make you aware of some control commands that LAMMPS has. We won't go into depth, but it might be useful for you to know about it. So we've used these variable equals before. There are other keywords you could use here, but this is if you want to set a variable once and then use it. For example, if you want to change the temperature everywhere, and you can use the variable name on names of files like we did with density, so that they're all saved differently and they don't override each other. It's a very useful thing to do. You can then set a variable by using the delete keyword, and you can then, inside LAMMPS, you can do loops using indexes. This can be quite complex, but for example, if you want to run the same simulation at 5 or 10 different temperatures, it can be useful to just write a loop and have it do it all in one go, instead of having to submit 10 different simulations. The syntax is here. It's not the simplest thing. I don't expect you to get it the first time, but if you are aware that it exists, at some point you might remember, oh, how did I do that? Go and look at the LAMMPS manual and read a little bit about it, and then you can easily make a loop if you need to. You can do a loop over an integer, or you can do a loop over a number, an array of things that if you want to do several different temperatures, for example, you could put all the temperatures that you need here, and then use the variable inside your loop. We should go on a break for about 30 minutes, so we can come back at 3:40. In the meantime, if you want, and I would recommend you do the reruns. To do that, you will need to change the submission script again. The command is here. This command will launch the rerun. And if you want to continue, have a go at RDFs or have a look at the mean square displacement, for example, have a go at that. Try the restart command as well. I'll be around if there's any questions. Just ping me in chat, and I'll answer. And I'll see everyone back in about 30 minutes. Hello again. Welcome to the last session. We shall talk a little bit about GPU acceleration, a little bit about some other tools that you can use related but not exactly inside of LAMMPS. And then we have some time for some questions if anyone has any. Let's start with GPU acceleration then. LAMMPS has two main packages that can do GPU acceleration, and they behave differently. There are historic reasons for that. They support different pair styles and bond styles and stuff like that, and they also support different providers of GPU at different levels. A rule of thumb, the GPU package, it's just called GPU package, has better support for NVIDIA GPUs using CUDA, and the Cocos historically has had better support for AMD GPUs. However, technically, both kinds of GPUs should work with both. We have found on ARCHER2 that the Cocos package works better with the GPUs we have there. On Cirrus, we use the GPU package with the NVIDIA V100s that we have on Cirrus, for example. Your mileage will vary wildly depending on what kind of simulation you're doing and what kind of GPU you have access to. You might need to check whether the compute or the fix or the atom style that you want to do is available with the acceleration that you want. In some cases, if it doesn't exist, the fix will be run on the CPU, but in some cases, LAMMPS might just refuse to run your system at all. So you'll need to double check that. For the example that I prepared for today, everything can run on the GPU. So we just use one MPI thread, and then that offloads all the work to the GPU until it gets back. Let's have a look at how you could do that. The syntax between both the GPU and the Cocos package is not exactly the same, but it's very similar at a higher level. So if we have a look, the input file will be exactly the same that we've been using so far, the LJ fluid, but the submission script will be very different. Firstly, changes to the SBatch commands, and this is an ARCHER2 specific thing. You cannot tell Slurm how many cores you want. You'll always get a percentage of the node depending on how many GPUs you want. You just ask how many nodes and how many GPUs per node. So in this case, I'm just asking for one GPU in one node. This is the exception to the case that I told you this morning about the GPU nodes can be shared in ARCHER2 when none of the CPUs are. So if we compare to the submission script, on the left we have the submission script that we use for exercise 2, and then on the right we have the GPU submission script. We can see here that these 4 lines do not exist anymore on the GPU submission script. So you cannot ask Slurm for these things. Slurm will refuse to launch your simulation if you add any of these. What we do is we add this information to the srun command down here. So you need to add this information directly on the srun command rather than on the entire sbatch script. So that is the caveat. Because I'm only asking for 1 GPU, I am only asking for 1 task. If you were asking for more GPUs, you'd ask for as many tasks as you needed. 1 per GPU should be fine, although you could do some OpenMP offloading as well. We won't be covering that today. That's usually a topic for the advanced course. The other changes that you can see here would be the partition. You'd be using the GPU partition instead of the standard. And the QoS, the quality of service, would be using the GPU-shared. If you're using the entire node, for example, if you're using 4 GPUs, which is the maximum on a node in ARCHER2, you could use the GPU-exclusive or EXC to have the entire node for your stuff. I mean, if you just want 1 CPU, 1 GPU, but want the entire memory, for example, you could also do that, but that is a little bit, you'd probably be waiting on the queue a little bit longer. I believe the limit for the GPU partition ARCHER2 documentation. The module that you load is slightly different. It's LAMMPS-GPU instead of the regular LAMMPS. We only have the 1 version right now, but as newer versions of LAMMPS come out, we might compile and install more recent versions of LAMMPS with GPU support on ARCHER2. And then the last thing that is different is, as you can see here, the not only the tasks that you pass to, not the tasks, sorry, the flags that you pass to srun, which is here on the first line, but also the flags that you pass to LAMMPS. So you have these extra bit here, -k, that stands for the Cocos package, and you turn it on. Cocos can offload to CPU as well as GPU, so it can do some of the things that OpenMPI does. Here we just want the GPU portion of it, so that's what the G stands for, and then we want 1 GPU. If you were running this on more GPUs, you'd have to increase this number here as well. So you'd have to increase the number here on the number of tasks and up top here when asking for GPUs. Then the -pk for package Cocos, and then the -fx, that's the sensor suffix Cocos, that appends the Cocos suffix to any of the pair styles or atom styles or bond styles that have the Cocos acceleration. This automatically appends that, so that means you can use exactly the same input file that we've been using so far. If you didn't want to do this, you could go manually and add all the suffixes to all the pair styles. For example, instead of LJ-cut, you do LJ/cut/KK. But in that case, you need to change the input file. This just allows us to reuse the same exact input file. Launching the job is the same, just sbatch. And we should then see it run on the queue. I can show you, while we wait for that, I can show you the difference for the GPU package. So on the course material, we have the same command for the Cocos. On the GPU package is very, very similar. We don't have the -k. We just have the package GPU and how many GPUs you want. and then the -fx, the suffix is the same idea as the -sfkk, but it's GPU instead of kk. Then the end of it is exactly the same. It is now running. It shouldn't take more than a minute, I think. For this specific case, I did increase the number of atoms that we are simulating, otherwise it would be over in about a second. So instead of a 10 by 10 by 10 cube, we have a 50 by 50 by 50. So that's 125 times more atoms than the previous exercise we were doing. Oh, that's going to take another few minutes. Oh, this is longer than I thought it was going to be. Well, in the meantime, I can show you the VMD then. If we go back here, yes, we have VMD available as a module. You'll run into the same issues in terms of opening windows as we did with GNU-plot. So you need to have that -x flag when you log into ARCHER2. But if you launch VMD, after a while, it always takes a bit to load. You should get some windows, this one, and the main menu a little bit afterwards. So this is the main GUI for VMD, and that's the main display window. You can try and have a look at loading a molecule if it allows me. It can VMD over SSH can be a bit fiddly. If this doesn't work, I can open my local executable. So new molecule, and that pops up this window. Finally, after a while, this shows up, and we want to open NVT. There we go, and it shows you a bunch of random lines that we have no idea what they mean. Here you can see it's the timeline, so we have 500 time steps to choose from. If I go back to 0, we can see that this looks a lot like a square cubic lattice. That's because it is. We can change the representations of the atoms to be Van der Waals surfaces instead of lines. By doing that, for example, and then if I bring their size down, we can start to see the cubic array. So VMD is extremely powerful. You can rotate and you can translate it, and you can do everything you want to visualize your system. You can play back the trajectory at a certain speed. I'll guarantee you that if you download VMD to your machine and then read the trajectory from there, it's going to be a lot smoother, unless the system size is so large that you have no other choice. VMD is incredibly powerful. You can render images and movies from it. You can calculate things. It can be extended by plugins. There's hundreds of hours of content on VMD alone. But even just to open up a simulation like this and have a look at what happened to see, for example, if your simulation crashed, but you have a little bit of the trajectory to see what atoms exploded. It could be a way of checking what is going wrong, or starting debugging what's going wrong. So as well as changing the type of drawing method, you can also color the different atom types of different colors, for example, to render images and stuff like that. You can render incredibly complex and beautiful images and movies from VMD. And it's available on ARCHER2. You can also run VMD without the GUI. You can just run it directly from the command line. That is especially useful if you already have the commands that you want to run in terms of scale it to this size and change the configurations to this, and then render the images from this point of view. So you can do a lot of scripting. The language is TCL, TK. It's a bit outdated, but if it's an extremely large system that your local computer can't even open the display, which can happen with extremely large systems, then that might be the way that you have to go about it. But that was what I wanted to show you on VMD. If no one has questions about VMD, I'll go back to the GPU output so we can have a look at that. Okay, doesn't seem like anyone has questions, so I'll close this. It's going to take a while. Okie dokie. So that should be finished. Yep. Okay, so if we have a look at the log file, we can see that the information here at the top is slightly different. It tells us that LAMMPS was compiled with Cocos version 3.7.2, and it's using 1 GPU per node, which is what we asked. It is telling us that it's loading the Cocos package. And then we have a bunch of the same information we had before, except that we now have 135 times the number of atoms we had before. The neighbor lists, all of that is pretty much the same. And then we get the thermodynamic information the same, but then at the end, I was going to say we should have had some GPU-specific information, but I guess that only happens with the GPU package. Sorry, Cocos is relatively new for me. I did most of my work on the GPU package. So usually you get a breakdown on what types of, on the memory that each GPU, that was used on each GPU. I do notice an extra line here, but that is not what I was looking for. I was expecting a detailed breakdown, kind of similar to the MPI one, but more on the memory that was used by the on the memory used on each GPU. I think we have enough time. We can do a quick exercise. I told you what things you need to change on the submission file, but have a go at running LAMMPS using the GPUs. Change the number of GPUs that you run. Try 2, 3, try 4, so that we don't wait too much. Maybe decrease the number of atoms here a little bit. Do something like 30 on each side, something like that. Should be low enough that it runs in about a minute. Yeah, I'll give everyone, I don't know, 5 minutes to do this exercise. Try it with 2 or 3 GPUs and see how that goes for you. while we finish, I'll just show you what some of what lamps can do. Sorry, VMD. This is the output from the ethanol simulation in the first exercise. So what we can see here is at the start, we have these lattice with lots of empty space between the edge and the main, and this is why some of the decomposition between cores will be very, very bad, because there's a lot of space on part of this simulation, a little bit on purpose to make sure that you learn a little bit about the balance command. And if I slow this down and I start playing the simulation, you see that as time goes on, the ethanol starts expanding, and if enough time, given enough time, that the ethanol would fill up the entirety of the box. So this was some very simple changes to just the color of the van der Waals surfaces. You can get much more into the options of this, including the direction of the lights and what kind of perspective you want to see. There are representations for ribbon, for protein structures. There are, for example, stick and ball representations that can be useful sometimes. Be this one. Although if you don't edit the bonds between the atoms, you can get some quite random bonds. So that can be fixed as well. So yeah, VMD extremely powerful, and it's much better if it's running on my local machine rather than across the internet with from Archer. But my local machine would not be able to load the same amount of big systems that Archer would. Okay, any issues with the GPU exercise? Any questions? We are approaching the end of this course. Some other software that might be of use when you're generating topologies to run on LAMMPS, or when you're analyzing the outputs of LAMMPS. PackMol is a great tiny terminal tool to pack thousands of molecules together in one box that you can then pass to VMD to set up your inputs. It gets some used to. There are some examples on the course materials on the extra chapter at the end on the syntax on how to do it. Ovito is a visualization tool like VMD. It's the basic version is open source. It's loved by the more on the engineering side of scientists. They use it a lot more. The tools are more suited for their needs than VMD are for my chemical and my physical colleagues. You can also use two Python packages, MD Analysis and Pylat. They both have functions to read LAMMPS topologies and trajectories, and then calculate a variety of properties from that and convert them into other things and create new data files from that if that's what you need to do. I'm sure there are more that I don't know of, but these are the major tools that people that use LAMMPS use regularly. Well, thanks everyone for attending today. We are a little bit early, so if anyone wants to have a go at the PACMOL, there is an extra exercise, exercise 5, that has all the files you need. And then if you come here to episodes and go to creating a topology, you can get the instructions on that. I'll stick around until 4:30 to answer any questions. Next steps, we have advanced ARCHER2 LAMMPS course. I don't think we have a set date when we're about to run it, but we do have a recording from the last time we run it some months ago. I forget exactly when, maybe January. You can always find all the recordings of our courses on the ARCHER2 website. If you come to training and you go to past course materials, you'll have an entire list of all the courses that we ran. Everything that has the video symbol over here includes links to the recordings, like this course will be recorded. So if I advanced use of LAMMPS, that's the one who was in January. My memory is still not terrible. So if you come here, you'll be able to find the recordings of the previous time we ran it. You'll also have access to the course materials. But we do plan to run it sometime soon. I just don't know exactly when yet. Keep an eye on upcoming training for all of that. We do our weekly newsletter from ARCHER2 also tells everyone what upcoming courses there are. If you're not subscribed, you can do so from your Safe account. Finally, these TA176 will be available, I think, for about a month or so after today. Do not leave any files that you might need there. Take them somewhere else, because in about a month or so, all the accounts will be deleted permanently and without any further warning. There is some small budget on TA176. We're happy for you guys to keep using whatever is left. It's going to be 20 CUs or something, so it's not a lot. But if you keep running, if you want to run the exercises again tomorrow or the next week or something, that's absolutely fine. As always, we have a lot of the information on the ARCHER2 documentation, ARCHER2 manual. If there's any issues with the content of today, do email me directly. My email is on the course material on the first page. If you have any issues with ARCHER2 itself, email us at support@archer2.ac.uk, and me, William, or someone else from the CSE team will reply to your emails with some help. That's about it. You'll get an email, I'm sure, very soon asking for your feedback, not just how well you thought the course was taught today, but also if there's any particular session of the course that you would have liked to be a little bit more in depth, or some things that we didn't cover that you would have liked to. We can take that into account and next time add it to this course. Some of the more advanced topics will be covered on the advanced course, though. Wouldn't be useful on an introductory course. Yeah, like I said, thanks everyone. I'll be around another 15 minutes or so, answer any questions that anyone has, but thanks very much for coming.